Welcome to a Stationeers coding video on Vulcan automatic or degassing through a furnace. And have a little test facility here. You can see our furnace and chip, and we'll go over this in a minute. And what you see here are some ingots and various ores that I went ahead and cycled through for testing purposes. And while I'm here, I'm going to show you a really cool trick. This is a large power vent set up here. And note there's no pressure here. If I remove this wall, notice that where I'm standing, it's still nil. If I go outside or outside, we go inside, it's nil. If you go right here next to it, you get a little bit. So as a bonus, this is a doorless airlock. Pretty cool. Now, funny thing about this, it doesn't work with a door. If you leave the door open, you will not get this same effect. It only happens when there's no wall there. So I imagine what's happening, the logic that passes gas through empty frames, it's much slower than passing through a door here. So if you ever got tired of using doors on Vulcan, you can just set up a large power vent, cost you power, like in a workshop, and heck with it. Take the wall out and you got instant magical airlock. Obviously a bug, but all right, so I'm going to switch over to daylight so we can see the system here. So let's take a look at the configuration first. So we have the old IC chip housing and IC chip running. We have the computer, which is only needed for programming. I have an advanced furnace with both connections. And the output of the furnace, just a simple set of chutes. And we'll look at the back in a second. The input actually is routed to an advanced hopper, and the power and data cables are snaked down here. So that's what we got here. We have the gas sensor, which is outside, the advanced furnace, which is right there. We have the advanced hopper, which is sitting right there. And we have an active vent, which is outside, and I'll show that in a second. So let's zip outside here. So we see the gas sensor, which is so we can monitor temperature outside. We have an active vent that's set up to the input vent. And we have just a cowl on the output. So the reason for the active vent, if you just put a cowl on here, the inflow of gas is extremely slow. So the active vent is used to boost the pressure to speed up the rate of gas moving into the advanced furnace. The chip controls both this. It will reprogram this to switch the mode and turn it on as needed. It seems that when you pump gas out, since the pressure is really high, it's quite quick. So there's no reason to assist this. Okay, and then we have a set of chutes that go all the way up to the hopper. Now in this case, you probably could have nested this a little closer and used fewer chutes, but I just kind of spaced it out here for the design. Just a standard hopper. Also, I don't have it on this configuration, but I recommend putting maybe 4 walls around this. That allows you to put even more ore in here. I didn't do that just for the purpose of demonstration. All right, so kind of back up a little bit and give a better view. So hopper shoots to the input, advanced furnace, cowl on the output. On the input, we have an active vent, and we dump the stuff inside. Now, since we don't need actual manual access to the front, that furnace could be anywhere. It doesn't have to be, through the glass like that. You can stick it way over here or wherever you want to put it, up on the roof, because once the system is set up, you don't touch the furnace. my little testing room. As I said before, the chip fully controls the furnace, except for maybe for debugging purposes when I kind of watch it. You can put it anywhere, enclose it, hide it, whatever you want. All right, so let's look at the code. As always, the code will be a link to a GitHub repository. And so if there's any updates, I'll just apply it there. Now, unfortunately, this code is a bit long and there's some heuristics involved. And it goes on and on. There's 127 line limit, so we got pretty close. Now, this is pretty verbose with commenting spacing, so if I really had to compact it, I could do that. And I looked at this code, played with this code for a while, and this seems to be a reasonable implementation. There's some scenarios where, if the pressure is this, you turn something on and off. Very simple. This is actually one of the more complicated scripts. It's surprising. It actually is as complicated as this happened. So, all right. Now, if you break it down piece by piece, the code should make sense, and let's go through and explain it. So we have some defines here. We have the minimum ore feed pressure and temperature. So this is the pressure and temperature of the furnace for ore to be released to the hopper. And technically this only has to be 1 kilopascals, or 100 kilopascals, should I say. And this is 100 Celsius. They're higher when I want to have more gas in there in general. The reason it's higher is that if you put it right to the limit, like say 100 Celsius, and you drop coal in there, the temperature will drop and only some of the coal will be degassed, and the other parts of the coal will not be degassed because it goes underneath that temperature. So as I said in the comment, I try to make the minimum a little higher than the actual game minimum to give a buffer, so when it sees the furnace at this condition, no matter what it throws in there, even a couple, it will be able to degas that successfully. Then the logic will kick in, realize it's too cold, and deal with it. And that's why these are a little higher than the game minimums. I have two constants that I sort of try to maintain the furnace between. The values are arbitrary. They seem to be reasonable. Nothing more than that. I wouldn't go too high, but that seems fine. I have the port devices. So as I looked at, we have a sensor, which is sitting outside, furnace, which is the advanced furnace, a hopper, which is the hopper is two versions of it. There's a standard one that has no electronics, and there's the advanced version. It's actually the same kit, so there's no additional cost for the advanced hopper. And then we have the active vent, which is also sitting outside. We have quite a few state registers, and this is my typical pattern. And the reason I do this is that way, when you see these registers all over the code, you kind of know what they actually are for. And this becomes a problem. The code becomes very, very complicated. Of course, you run out of registers, but in this case, I fit them all in there. And I reserve 0. I go from 7 to 14. R15 is actually RA, so you got to save that. And then 0 through 6 in this case are basically work variable, temporary variables that are used in that scenario. All right, so we have, is basically these two match these two. Effectively, is the furnace pressure okay and the furnace temperature okay to feed ore through? So they basically map to that. Does the furnace have input? So basically the furnace itself has two slots, an input and output. And if it's a middle processing something, there's a slot 0 that there's a piece of ore waiting to go through. And the one thing I do not want to do in design is have too much ore flow through. And the reason for that is that the furnace stays, the lever on the furnace stays open. And if I just let it flow through without controlling the rate, if the furnace gets too cold, then you get a bunch of ore going through that's not been properly degassed. Reagents effectively is a count of things inside. So if it's a middle of processing something, then reagents will be non-zero. And I use that also to say, well, if it's in the middle of processing something, then don't dump anything through the chute. The chute system is not designed to be super duper fast because it does take time to re-warm up the furnace. And when you mine, you can only mine so quickly. So there's a couple seconds between each block of ore. That's to give the system a chance to stabilize and these various variables to have valid values. We have the low and high of the furnace itself, which are these two values. So if it's lower than that or higher than that. Is the furnace hotter than the world? This is useful because if we're in a condition where the furnace is actually hotter than the world, then we want to avoid bringing gas in if we can. If it's the opposite and the world is hotter than the furnace, it kicks into a mode where it exchanges gas. It'll exhaust gas and bring in gas simultaneously. This does seem to work pretty well and to slowly raise the furnace. So there's a scenario where I dumped a bunch of ore in. It got during the morning time. It degassed it all. And then effectively it was empty. There's nothing more in the hopper. And the furnace kept getting warmer and warmer because this was false. The world was hotter than the furnace. And then it just kept exchanging gas and the furnace was going up in temperature, which means it'll be in a better state in the next batch of mining ore to the point that some of the ore will just smelt into ingots automatically, which is nice. Now, in this case, I would say the name probably invert. I should probably have, is the world hotter than the furnace? I think that makes the logic a little more easier to read. And so this is a point where naming things poorly, like I did in this case, can make the code a little more difficult to read. Now, I've gone through and tested all this stuff, so I'm not going to change it now, but it's a good point out that the naming could be inverted. And one useful thing when I go through this code, I'm sort of doing another self-review of the code and look at names and did it make sense or not. So I think that name's probably not appropriate, but we'll go on. And is the world temperature cold? So effectively, is the world colder than this temperature? If it is, don't bother bringing in gas, no matter what. Just don't bother because it's too cold and, it's not going to help the situation. And, all right, so that's a lot of state because a lot going on in doing this. All right, so we have initialization. Basically, put the furnace in a known state, turn off the inputs and output, turn it off. We'll set the lever open on the furnace. The reason is this is not designed to create alloys. We never want to take the chance of like iron and copper mixing together. With a more advanced logic, you could probably do some clever things like if you know the next ore in the hopper and you want to mix it and the temperature and you go, we can smelt this and blah, blah, blah. This is not that code. This just does avoid all that fun and games. The hopper, the open is set to 0. That's typically hopefully the default. If this is 1, that means all your ore is just flowing through. So this hopefully should be redundant. We have the vent, which we turn off, and we set the mode once. We only bring in gas in. We never use to exhaust. And I set the internal pressure to 10 megapascal. Although realistically, this is really not needed. If you turn the vent and the furnace on full bore to bring gas in, it does seem like it will not overpressurize the pipe from just playing around with it. This is just a safety thing, so why not drop it in here? All right, so I have a sleep instead of a yield because this is not that timing critical, so let's slow it down a little bit to save CPU resources. And to some degree, we don't want this operating too quickly because we want the system to stabilize and when we read the value, so when we drop ore through, we know the furnace is in a good state. So this is getting a little bit complicated, so I tried to break this up in some subroutines. And so the pattern here, if it has FN for function, that means it returns. So basically you call it with a link and it returns by jumping to RA. If it doesn't have that, then it does not return. So in this case, this jump means this does not return. It just made the code a little easier. If this was a higher level language, I wouldn't be doing this. And this is sort of the fun part about using this assembly language. You can do some really bizarre tricks. And that was basically kind of reduced number of lines of code. All right, so we compute the state, we see if it's okay to feed ore to the furnace, and then we manage the furnace gas. We have a lot of state, so this should be all straightforward, nothing you haven't seen before, just a lot more of it. So for example, the pattern always is, we grab some value from some device, we compare that to a constant, and we use that to set a register, which we treat as a Boolean value effectively. So we grab the furnace temperature, we do some comparison, we grab it if it has reagents. That's how we check that. If the furnace slot 0 is occupied, which means there's something in the input waiting to flow through when the furnace is complete what it has now. I re-grabs a couple of things just to make the code simpler. I don't hate to carry temporary variables too far, because if you add something in there, you could break code. So I reload these values. So the furnace temperature and the sensor, which is outside, that's how I determine if it's too hot. The furnace is hotter than the world. And this is the check to say, if the outside is too cold. So this is below the feed temperature, then we're too cold. And then we return back up to here. Then we determine if we need to feed ore in the furnace. This is pretty simple. So if the pressure of the furnace is okay, the temperature is okay, and it doesn't have any input, it's not doing anything, cycle the hopper. So this, as far as I know, how you cycle the hopper. You open it, set to 1, yield, close it. You got to have the yield between these two, or this will not work. Then I decided to just put a sleep in here just to let that ore kind of flow through the chutes a little bit. If you have excessive number of chutes, you may need to increase this value a little bit. And then returns. To some degree, you could split this code into 2 chips. One chip just deals with should I feed or not, and one chip that managing the furnace gas, but then you have 2 chips. So this code is the part that manages the gas is straightforward, sort of, but it's not pretty. If the furnace pressure is too high, we need to empty it. Now, empty furnace does not empty it all the way to 0, as this starts removing gas from it. And then if the furnace is hotter than the world, and this is where I have the opposite, this is we're doing 0. Basically, this says if it's not hotter than the world, then we need to heat the furnace. Otherwise, we drop down here to the turn it off, and we turn everything off, and we go back to main. So we stop adding furnace gas. The empty furnace is basically, so the input to 0, output to 100, turn the furnace on, turn the vent off, sleep. Give it a chance to do something here. Don't just do it for an instant tick and then go. Because if the pressure is high, we want to get it down a bit and then start filling up more gas. And then we return to main. So this is a case where this is not a function that returns. It goes back to main directly and processes it. Now, if this is written in a high-level language like, C++ or C# or Python or something like that, I wouldn't do stuff like this. But, okay. So now we go to heat furnace. So heat furnace, once again, we got to do some more checks. If the world's too cold, well, we don't want to bring that in. If the furnace pressure is too low, then we need to, so basically, if the pressure is not too low, because this is equal, so if that's 0, that means effectively not, then we go to here. So if it's not too low, then exchange gas. If it is too low, we turn it on. So effectively, if the pressure is below 10 megapascal, just turn it on, get some gas in it. We already know it's not too cold because we checked this here. And then indicates we're basically between 10 and 20 megapascals. The world is hotter than the furnace. Then we exchange gas, turn both on, turn the furnace on, vent on, and let it exchange. And that seems to actually work pretty well from playing around with it. And you notice I'm turning the furnace on and off. Technically, you don't have to. You can turn it on and just play with the settings. In this case, they go, well, I got the code. Just turn it on, save a little bit of power. It's also useful for sort of debugging because you can kind of watch it and see if it's actually powered up or not. Turned off, if the pressure, if everything in the furnace is okay, it still will cycle ore and dump them without being turned on. You don't need to be turned on to add or remove gas from it. And that's it. So unfortunately, this is not simple, straightforward code. It's a little bit to it. You look at any individual like area, it should make sense, but in all together, it does some stuff. And this is like my second iteration of it. And I was attempting to try to make it simpler. The problem is doing something pretty complex, more complex than I thought it would be doing. And then we're kind of limited to this IC language, which makes the code even more interesting. I've done limited testing in it. It could be bugs in it. It seems to work fine. It seems to work better once you give it time to get up to temperature. So like, if it's not actively doing anything and it's just sitting through a hot day, it does heat up. As I use it through the playthrough, that'll give me even more testing with it. But I did a little bit of testing and it seems to be happy. All right, so that's the end of this video. I hope you find this code useful. And more importantly, part of this video is not just trying to solve unique problems within Stationeers, but hopefully to teach a little bit about IC coding from example. Here's where I do it. And I'm definitely not going to claim I'm the best coder out there. Especially this one's not great. All right. So until next time, see ya.